Yeah, welcome again to our first talk. So yeah, we hope that these talks can provide less formal interactions between external experts and UCLA students. After the talk by our distinguished speaker, you are encouraged to ask questions, so feel free to prepare your questions and ask afterward. So today we are very honored to have Dr. Josh Rigler at the U.S. Geological Survey to be our first Smart Talk speaker. Josh earned his PhD from the University of Colorado at Boulder, Department of Aerospace Engineering Sciences. Drawing on this applied math and physics background, he has since employed the modern numerical methods in multivariate statistics, data assimilation, and machine learning to solve key problems in space weather hazard analysis and forecasting. His research interests and contributions literally span from the sun to the mud. For those who are not familiar with this term, this basically means all domains between the sun and the lithosphere underneath us. Josh's work covers multi-spectral solar image feature classification, solar wind radiation belt, dynamical coupling, magnetosphere ionosphere coupling, and for the past 10 years, geomagnetically induced currents, GICs, in Earth's ground level technology infrastructure. Dr. Rigler is currently a research and development geophysicist in the geomagnetism program at the USGS Geological Hazards Science Center in Golden, Colorado. Josh and I know each other for many years, and we work together through our participation in a steering committee of NSF's Global Environment Modeling Program, or GEM program, where he plays a critical role in the communication between USGS and the space weather community. Without further ado, let's welcome Dr. Rigler to give our first Smart Talk. Josh, the floor is yours.
Well, thank you, Peter. I will attempt to host disabled participant screen sharing. So,
okay.
I probably should fix that while I just talk a little bit.
Okay.
And so today, first off, thank you for that kind introduction, and thank you for inviting me to speak to this group. And I have actually had a rather broad exposure to space physics and space weather over the years, and it's been really interesting and exciting, and I think educational. Just because, I mean, all of this is educational, but I think the opportunity to be exposed to so many different technical disciplines, scientific disciplines, and all sort of targeting this one overarching objective of being able to understand and predict space weather I've been really fortunate to be able to do that. And so I'm going to try to share my screen again.
Oh, yes, I think I just reconfigured it.
Let's see. I think I'm gonna.
Oh, okay. I think we're.
Oops, I got my whole big screen, so I'll go ahead and bring up my PowerPoint presentation. And how does that look?
Oh, yes, yeah, full screen.
Excellent. Okay. So today I want to talk to you about staying grounded with geomagnetic observatories. In a nutshell, this is more of an overview of our program, our operations, and our research. Ground magnetic observations, and maybe especially those from observatories, but certainly any ground surface magnetic measurements can play a really important role in understanding our near-Earth space environment and being able to actually predict mitigate space weather hazards. So without further ado, I'll move on. So I'm going to just give a really, really brief overview of geomagnetism, and I hope this isn't too simple for most of you, but this is bear with me for 2 slides. This won't take long. First, the Earth's main magnetic field, the thing that I think we're all familiar with. We've all used a compass, or at least used the magnetic sensors inside our smartphones. This is something that's driven by a dynamo in the Earth's liquid outer core. And while we don't understand all the details of how that dynamo works, we do understand what happens on the surface. And that's a rough dipolar field that helps to orient magnetized devices like a compass so that we can actually navigate. And we've been doing this for hundreds of years. But I think most of us also know that, that the Earth's magnetic field is neither dipolar perfectly, nor is it stationary in time. And this figure on the right, it's showing you how it's not dipolar. So these are contours of magnetic declination that change across the northern hemisphere. And more to the point, maybe, or maybe more just to add to that, stationary. It actually varies time, but these are fairly slow variations, and we can track these. And this is part of what magnetic observatories do. They track these slow changes, the slow evolution of the Earth's magnetic field. But they also can detect, especially with current modern technology, can detect fast variations. And in fact, we've been able to do this for Carrington event in 1859. There was a huge solar flare that just a few days later caused some major disturbance in the Earth's magnetic field as it was being measured at the Greenwich Magnetic Observatory in London. And that's what this top figure is. And maybe more importantly, rather than not just seeing these variations, but seeing that they correlated with features on the sun, actually kind of opened the door to what we think of as modern space physics. And so this figure on the lower right is a picture drawn by Carrington, Richard Carrington. And if what the black patches are what he saw as sunspots on the sun, and we're probably all familiar with those, but he also saw these brightenings. And I hope you can see my cursor. In fact, maybe, let's see, I'm going to try to do the laser pointer here. I can't remember how to find that. Oh, okay, that's all right. Oh, there it is right there. Okay, so these little white patches here were extremely bright solar flares that Carrington saw, and was able to correlate those with the changes in the magnetic field that came along a couple of days later. Well, really less than a couple of days, maybe less than a day even. So the birth of here's, oops. Sorry, I'm trying to get the screen to change. Oh, let's use the keyboard. But the magnetic field, the Earth's magnetic field, is more than just declination. It's more than just the deflection in the north arrow on a compass. It is actually a 3-dimensional vector, and we can measure that in Z. X is a vector component. We also talk about it in terms of the horizontal intensity, the declination, and the inclination, so the angle with respect to the horizontal. And we measure those, or at least one way we can measure those, and the way we measure it in most geomagnetic observatories is with a 3-axis flux gate magnetometer. So a flux gate magnetometer does a really good job of getting high time resolution, fairly precise, or sometimes very precise depending on the frequencies you're interested in, measurements of the magnetic field. And then what we do with a geomagnetic observatory is we actually periodically recalibrate this sensor by taking field see over here. So we use some very specialized surveying equipment where everything has been demagnetized, and we use this to figure out the orientation of the sensor with respect to known markers in the field. And so we do because temperature, sometimes humidity, sometimes just the changing magnetic field itself, all these things require that we need to recalibrate our sensors fairly regularly. And there's two things that we see. There's a secular variation, which is the slow changing magnetic field that we sort of saw in that earlier video. But there's also this sort of seasonal change in the magnetic field. And so for the things that we want to do with these magnetic fields, we actually need to remove these variations. And these variations aren't huge. They're maybe on the order of tens of nanoteslas, but they're enough that we want to do this right. And so that's what we do with a geomagnetic observatory. But what is a geomagnetic observatory, or where are geomagnetic observatories? Well, the USGS has 14 of these, and they're geographically distributed across the sort of northern and western hemisphere, or North America, the North Pacific, and the Caribbean. And so we have kind of a high density of observatories in Alaska, because that's where a lot of there's a lot of aurora there, which are reflective of space weather that we're interested in. We also have a fair number across the continental US, although, as we're going to see shortly, maybe not as many as we would like. We have one in San Juan and Honolulu, and we have one all the way out in Guam. We also have one in Boulder, which is close to where I live, and one in Fresno, which is not so close to where most of you probably live. So actually, we have them literally in the Arctic, Barrow and Deadhorse, well above the Arctic Circle. Also subarctic, College, Shunigan, even Sitka, Alaska. And we also have them in the desert, Tucson, Arizona. And so there's problems that arise both from the extremes in these climates and problems that arise just from their remoteness. And we even have them in fairly tropical. So here's a picture of our observatory in San Juan. And while these seem like they might be really nice to visit, and they are, they can pose operational problems. There's lots of flora and fauna that you have to stay on top of. You have to regularly mow these lawns around the observatory so that we can actually access it. And this can actually influence our data if we're not careful in how we do it. And then there's also a general problem with the encroachment of civilization, urban encroachment, suburban encroachment, also military bases. Many of our observatories are located near military bases. And so these can actually introduce cultural noise into our data. So we have to minimize that and correct for it as much as possible. And so in terms of space weather, sort of traditional space weather, at least up until maybe the last 20 years or so ago, was largely revolved around global indices that sort of were a global measure of what was going on with the magnetic field. And so one of the oldest was something called the planetary K index, or KP. And so we contribute to that with our Fredericksburg and our Sitka observatories, which you will be able to see circled here. And so this plot that's zoomed in from the left is the KP index, which is sort of a log-scaled index that attempts to normalize things for different locations. And it gives you a measure of just how active overall the magnetic field is, how much it's changing. And some people will use this actually a proxy for whether or not you might see aurora, especially at lower latitudes. Another index is the auroral electric jet index. This is an index of high latitude observatories. And so our College and our Barrow sensors actually contribute to this. I think, if I remember, there's maybe 12 sensors that contribute to the standard auroral electric jet index. And so 2 of the 12, that's a significant contribution. But these are actually measuring the influence of high latitude ionospheric currents that are flowing and are related to the aurora that we see up in Alaska and northern Canada, and also over Russia to a large extent, and Scandinavia. And then finally, everybody who's been involved in this has heard of at least once, is the storm time disturbance index, this DST index. It's actually 4 low latitude magnetic observatories, 2 of which belong to the USGS, Honolulu and San Juan, others being Hermanus in South Africa and Kakioka in Japan. And these are measuring what's known as a ring current. So this is not an ionospheric current. This is actually an electric current that flows quite a ways out from the surface of the Earth, but it encircles the entire Earth and causes, can cause latitude observatories. And so these are all very interesting. There's a lot of historical context. There's a lot of research that on these, and it still depends on these to provide global context. But I would say in recent years, we've really been moving more toward localized magnetic fields. I mean, all magnetic fields on the ground, and we do our best for that locale precisely. But it hasn't, the data from these has not always been easily and readily available, especially in real time. And seeing as this group is about surface magnetic assessment in real time, maybe this is kind of important. So the USGS has a number of tools, but probably one of our most recent tools and most useful tools is our web-based data service. And so I'm just gonna, rather than try to do a live demo, which never goes well, I'm just gonna play this recording I made. But basically, you can get from USGS any of our observatories, any of their different channels, plotted on a single plot, a time series. You can zoom in and out on that time series. You can hover over that time series and see what the times are. You can see what the actual individual measurements are. You can add other observatories. You could have all our observatories in there. You can span forward and backward in time. Usually most interested in near real time, but you could go back and look years in the past. We have definitive data, which goes back decades. We have operational real-time data, which goes back years. So you really can access data through this tool. And maybe more to the point is you can actually click on this little details button and you can see metadata for the observations, and you can click on a link that'll pull up nicely formatted digital data that you might want to use in your own analysis. So that's it for that little demo. So where does that bring us? In recent years, the USGS has been a fairly significant player in, I wouldn't say this is new. We've known about geomagnetically induced currents for decades. And there's been some people that have been studying this for that long. But in the last 5 years or so, there's been a real push by the US government and maybe also by other international governments to better understand these induced currents in the ground that then can short through technological infrastructure like high voltage power grids. And so the USGS actually has 2 major things that it can contribute to these studies, in addition to being advocates for them. Well, so so let me take a little half step back. The GIC, the problem and the hazard there is the current that can flow through the technological infrastructure. Well, to a large degree, that's kind of an engineering problem. How does the infrastructure handle this unexpected current flowing through it? And while we do work closely with people in government and with regulators, we're really most interested in physical hazard, this sort of scientific topic. And so what that means is we're trying to predict geoelectric fields. What is the electric field measured at the surface of the Earth? So there's really 2 components to that. There's the magnetic field and its variations and its spectral content. And there is the ground conductivity. So how do we get an electric field at the surface of the Earth from a time-varying magnetic field? So I'm just going to do a quick movie here to show one of the things that I've worked on. And these are basically the magnetic vector disturbance or magnetic disturbance vectors, I should say, over North America. And they're interpolated using a technique based on spherical element current systems, or SECS. And this is a well-known technique. It's been used by a lot of people, a lot of researchers, and more a lot of operations at places like the Space Weather Prediction Center, as well as in industry. And this is just a way of interpolating between sparse ground measurements. And maybe it's hard to see, but I see there's our Fresno Observatory. There's our Stennis Observatory. There's 9 in Del Rio, Texas. There's Tucson, there's Boulder. And we also have some observatories from the Natural Resources Canada program up in Canada. And so we're fitting a set of physics-inspired basis functions to measurements and then interpolating based on those measurements. And these are for the 1989, March 1989 storm that actually caused a major blackout in Quebec. And this bottom plot maybe is less interest right now, but this is showing what the equivalent currents look like based on those magnetic disturbances. So we have a time series, or we have the spectral content from a time series of magnetic variations. And now we want to push that through an impedance tensor, a magnetotelluric impedance tensor. These are observations that are made not really only over a short period of time, because magnetotelluric impedances, the impedance associated with the ground conductivity, don't change much over time, but they can change substantially over really short distances. And you can kind of see that these plots are a little bit confusing. I'm not going to go into too much detail on them because I think I would these resistances. If you have a higher resistivity, you're going to have a higher electric field. And so if the ground is highly resistive, currents are going to want to short circuit through your infrastructure. They're going to short circuit through your power grids. And so it's places where we see a lot of resistivity where you're going to actually have the highest hazard. And so also over here on the East Coast, although it's a little difficult for me to see because I have my members of this meeting covering that up. But over here on the East Coast, we can see high resistivity. And what you'll also see, though, is there's a strong frequency dependence. These ones here, where you have strong resistivity at 120 seconds, the Earth is actually not very resistive at all at 1200 seconds, for example. And so this is why we can't just look at something like the simple dB/dt by people in the space physics community. This is also why it's been really critical to bring together the space physics community, research community, operations community, with the solid Earth geophysics community. Bringing these two together has allowed us to come up with new tools, new utilities that are being used in operations at places like NOAA's Space Weather Prediction Center as we speak. And so here's an example. It's not a terribly active time right now, but I pulled this off of their web page just a day or two ago. And you can actually see how the higher electric fields arise exactly where we expect them to, where we have those high impedances. And so those capture the spatial variation, but it's the time varying magnetic fields that would actually cause these things to go into yellow, orange, red, and even purple during large magnetic storms. And so this is an operational, near real-time operational space weather tool being used at SWPC. At the USGS, SWPC has sort of the real-time operations responsibility. We tend to focus a little bit more at the USGS on hazard analysis. So we want to look at long data sets and build up statistical models, statistical expectations that we might see a major hazard. And that's exactly what we've done in this figure on the lower right. Because the magnetotelluric impedances are essentially stationary in time, we have a long history of magnetic field measurements. We can actually do a historical analysis and figure out what the once in 100-year event looked like when mapped down onto the US power grid. So that was kind of a whirlwind, and I could spend an hour talking about any of those topics. There's other things we do at the USGS. We're currently upgrading and adding to our observatory system, new sensors and new data acquisition systems, allow us to get our data quicker, and more reliably. We're expanding our data services to include magnetometers that are co-installed at the USGS seismic network, which is quite a bit larger than our magnetic observatory network. And so, we actually hope to fill in a lot of the gaps in our spatial distributions. Along those same lines, if we can't, at least until we can really fill in those gaps, we can actually use research models to help constrain our interpolation. That's kind of what we're showing here, is some work that I did recently, where if we did just sort of the raw inversion and interpolation between these magnetic observatories, do a pretty good job if they're not too far apart. But when you start to get large gaps between the observatories, you see a lot of red where we're not predicting well. Green is good, red is bad. Well, if we can constrain the solution with output from research space physics models, we can actually improve our predictions. So much more green in that plot. And also, even though we have a fairly high density grid of these magnetotelluric impedances, the conductivity of the Earth varies over pretty short spatial scales. Sometimes kilometers or less. And so it's almost better to be able to model those impedances and then back out, I'm sorry, not model the impedances, model the conductivity and then back out an impedance from that at an arbitrary location. And so this plot here is just an example of some work a colleague of mine, Anna Kelbert, conductivity models over the US. And of course, we want to continue integrating these data and products into operational space weather forecasts and better space physics research. I think with that, I just want to open it up to questions and discussion.
Yeah, I have two questions. I guess the first one is with like ozone depletion or like the changing of the atmosphere, do we expect like more dramatic geomagnetic like space events or storms of that sort?
Yeah, that's interesting. I would say the answer to that, the short and dirty answer, because this isn't something I studied, is just no. But if we flip that over and we talk about how changes in the Earth's atmosphere might impact space weather itself, there are actually a number of people who are studying that. And so, right, ozone depletion is one thing that I've talked to people who are studying that. And it's not so much the ozone depletion that's causing it, but it's the atmospheric dynamics that lead to ozone depletion in the high polar regions that actually might be strongly related to space weather.
Thank you. My other question is about like solar cycles and how it varies from decade to decade. And from what I understand, we're at a very low point in like solar cycle sunspot frequency. And when we expect that to get worse, if our infrastructure is accommodating of that, the future changes.
I'm sorry, the last part of that kind of cut out, and I didn't hear the actual question.
Yeah, so for solar cycles, and the time spans they vary, they kind of get worse, and then there's a lull, and then the solar events get worse and not as worse. Sorry if I'm explaining it badly, but do our like current infrastructure that's like our electronics that are made now accommodate what could be worse in the future? And like, is there preparations made for that?
Well, I mean, when I can, I try to encourage my engineering friends and colleagues to think about these things. I know so the power grids are one sort of industry and technology that are definitely taking this seriously. After not doing so maybe for a long time. I think other forms of space weather that are related to what I talked about here, people are also taking seriously. So GPS signals from GPS satellites can be impacted, and so new technology, dual frequency GPS, things like that can help mitigate that. But sometimes the technology itself is enough, and we really need to be able to do a good job of predicting, or either predicting in time, so forecasting, or predicting in space, interpolation or modeling, to be able to help mitigate these issues. So I don't know if hopefully that
that clarifies. Thank you.
Okay,
Hi.
great.
Oh,
Yeah,
oh.
yes, go ahead.
Why did most of the graphs in the presentation focus on the northern part of the US? And then there was not much in the southern part. Is there just not enough data in the southern part?
I think so. I think maybe this is probably, is this what you're referring to?
Yeah, yeah.
Obviously, this lack of data here. That's exactly what it is. It is a lack of data, and this is actually something USGS is intimately involved with, along with Oregon State and some other partners, to go in there and make more magnetometers survey measurements. I mean, I didn't really describe what those are, but basically people go out with both some long wires and electrodes that they plant in the ground, and they go out with some magnetometers, and they measure the electric field and the magnetic field at the same time for maybe 2, 3, 4 weeks. And that's enough time to actually get a good sense of what that localized impedance is. And then once you have those impedances across that entire region, you can actually invert those for improved conductivity models of the below surface lithospheric and even mantle conductivities. And working to improve that. In fact, these are kind of data that these are from data that was probably up to date maybe 2 years ago. And then of course, as you all know, COVID hit, and so that slowed things down a bit, but we're now slowly starting to fill in across these southern states. And it's our hope that within the next year or two, we'll fill them all in.
Okay, thank you.
So no, excellent question though. Good eye.
I had a question kind of similar to I think Eric's first question, but just looking at the like disturbance distribution, and this might be like beyond the scope of what you guys do, but is there, I'd be interested to know if there like is any relationship or like correlation between like topography or the climate or kind of these other like atmospheric elements in the way the magnetic field is affecting things, or if it's kind of just independent and based on the actual you know, kind of field lines and space weather, if that makes sense.
I think it's mostly, that's me getting feedback. I think it's mostly the deep earth and solid earth that are affecting things. I think there are loose correlations in sort of regional topography that are associated with geological features. And so the sort of first generation of these, of like this map here, these are actually using measured impedances, but the first generation of this, which really isn't that old, maybe just a few years old, was using sort of surface, what we call physiographic feature maps to kind of organize, you know, where you would see this disturbance. And that works to an extent. And in fact, I think, at least as of the last I had checked into it, that's kind of what Canada is still using, although I know they're working to try to improve that with magnetometer measurements as well. So it's certainly, it is one way to do it. And I think better than taking into account anything about the conductivity of the Earth. But I think direct measurements coming from something like magnetometer measurements are really the way to go in the future.
Hey, yeah, thank you, Josh. So any more questions from students? Yeah, which are very encouraged.
Sorry, this isn't really much of a question, but I guess I'm just very fascinated in like the part of the presentation where you're talking about like how you can use research to like predict like magnetic fields. I think it's like the previous slide, or no, not previous, like 15. And like, I think I'm just like wondering like, how do you think like having more density of like I know you talked about having more stations here and there, like measuring can make these more accurate, but I guess I'm just like more interested, like how does that actually like work and translate into like, you know, like updating like a map, like,
So
yeah.
so it's mostly about interpolation. So when I say that, I think I'm looking at improving our understanding of the spatial distribution of these things, but also in time when I look at it historically and statistically. This probably doesn't help to forecast things forward in time. So if you're thinking of more of a traditional these aren't going to help improve that unless we can figure out a way to make a better what we call a nowcast. Use that to kind of set the initial conditions for a forecast model. And if we can do that, then I think more measurements on the ground, better interpolation methods, these could help with our more forward-looking forecasting type tools. In space weather, and I apologize if I'm saying something that's obvious to most of you, but our biggest advantage, I mean, we're at a huge disadvantage compared to the regular weather world in that we have so few observations, or at least in space we do. There's so few satellites measuring what we need them to measure. But what we do have is we have sort of lead times. We have satellites measuring things at the sun. We have satellites that are placed out in the solar wind and able to get us sort of measurements and beam it back at the speed of light faster than these events are actually hitting the Earth. And so, so that's really nice. But one of the things we haven't quite figured out yet, and that I hope but there are more and more people working on this problem, and there's a lot of hope that some of the modern methods in machine learning and artificial intelligence might actually accelerate this. But finding ways to take measurements where we can get them easily, with lots of them on the ground, and map those back into setting the state of these forecast models so that we can actually forecast forward in time with some confidence. I really think that's probably the next big horizon to get over. I'm having a hard time coming up with the right words. And but I think that'll be a game changer.
Thank you. Yeah, it's very like amazing. I don't know, like the scale of this like project, and yeah, it's just it's cool.
You gotta focus in on I have to. This is the way I work. I agree, but I do have to focus in on one thing and just kind of immerse myself in it for a while and try to really understand it. And I think I've been at it just long enough where I'm starting to finally get a good sense of, what is the bigger picture. And, it is fascinating. It's also a little daunting sometimes.
Yes. Of course, yeah, I'd like to ask, as a host, but I do like to ask questions for all the students here. That is because our SMART team has students from many different science and engineering departments, and of course, each of them has his or her own major. However, from your point of view and experience, what kind of a general knowledge, experience, or traits that you find very useful when you look at newly graduates, so that you encourage all students to try to acquire or develop some particular skills or traits?
Well, no, thanks for asking that question, because it is something that we struggle with, because and largely because we are largely an operational outfit, and we aren't necessarily, the majority of our employees are not PhDs. I'm one of only, well, I shouldn't say only, we have several PhDs in our program, but a lot of them are very focused on the operations side of things. So it probably goes without saying, computer programming. Just doesn't say you got to be a computer science major, but you need to enjoy it, and you don't have to be stellar at it, but you have to do it at some point. Likewise, I think build up your data skills. Learn about statistics. And again, it doesn't have to be really advanced statistics, but you should understand what a correlation function is. And also just working with data, understand that like as we get to where we want to be, which is having a lot of data, you can have some huge data sets. And yes, we have computers and we have hard drive that work with huge bandwidth, and yet it's still, at least in our world, we're not the ones that have actually been focused on big data the way maybe industry has for the better part of the last decade or so. So I think they're, familiarizing yourself there would be extremely useful. Now that's all really practical and technical and engineering wise. I think from a scientific background perspective, I think geophysics, space physics, any of these would work. And I think just having a solid grounding in it and a love of it is key. And so, I think our program this is there aren't no mathematicians as far as I know. And so that's not what we're looking for. We're looking for somebody that has, a solid background in physics or geophysics, but not necessarily super specialized. And I think a willingness to learn. And sometimes a willingness to get a little dirty. Less for us than my geology colleagues, but we do get out in the field quite a bit. So sometimes I wish I got out more, but but there's definitely people within our program that get out on a regular basis. So.
Okay, yeah, wow, that's great to know, and I'm sure that can be very helpful to all students, including those other your answers to more technical questions. Any further questions from students? Well, if not, I really appreciate Josh can spend time with us today. I think it's so precious, and it's probably the SMART project has been going on for almost 2 years, and I think it's probably the first time that we have such wonderful advice from an external expert, and this is really wonderful for us. And thank you so much, Josh, for your time today, and really appreciate your presentation and the first Smart Talk for our project. And of course, we look forward to working with you and others in this area of geomagnetic measurements whenever we can.
Well, thank you,
Yeah.
Peter, again for the invitation, and thank you all for your attention. And,